This is part 1 of the correlation and regression chapter. That's chapter 10. So what we're looking at here is we have two variables defined. In this case, we have number of police patrols and the number of gallons used by the police department. And our question is, are those two variables related? In other words, do the number of police cars driving around have anything to do or any influence on the number of gallons of gas that the police department has used each night? Well, we would think so, right? We'd think essentially the more police patrols cars are out, the more gallons of gas that the police would be using. Well, to illustrate or prove such a claim, we make a graph. The graph we make is called a scatter plot. This is a scatter plot right here. You have your x part and your y part goes together to make one point, and in a scatter plot we don't connect the dots. Do not connect the dots. Now, if we were in algebra class and we were looking for what we call a linear relationship, see the word line in there? What we would be looking for are dots that were laid out in a straight line, that literally we would connect the dots. And if they didn't do that, we wouldn't call it linear. Well, that's algebra. Algebra is a perfect world. And in the real world, things are actually kind of messy. So when we make a scatter plot and we look at the dots, we're looking for a pattern, not that we can connect the dots with a straight line, but I think I have one here. If I had a marker, say a really big fat marker, the question I'm asking myself is, if I had a big fat marker, could I draw a straight line that would hit all or most of the dots? Yeah, I can do that. I might even use a little bit fatter marker, but I can make a straight line pattern that would encompass all or most of those dots. If I can, that is a correlation. So when I look over here and say, is there evidence of a linear relationship, I'm getting that from my graph. Yes, there is. Now, I want to put some numbers to this. So down here, I have the printout from what happens when I have the calculator compute what we call the linear regression. Now, in your calculator, you're going to have two possibilities for that. I'll tell you which one you need to pick so that when you get your printout, you have the information in the order that it's going to be asked for on the stat lab and in the homework and the what am I trying to think of? On the test. Yes, the test. Remember the test? So anyway, I print this out. Notice it gives you equation of a line y equals a plus bx. That is the equation of the line that would actually pretty much go through the middle of your flat line, or of your fat line. It's again, it's not going to connect your dots, but it's going to be the line of best fit. It's going to be the middle of the road of your fat marker. The r and the r squared, those things are there to tell you how well your model fits a straight line. If I look at r, if I had this situation over here where I actually drew a straight line through all of my dots, that straight line through all of my dots, the perfect correlation, that would have an R of 1. So anything close to 1 is going to be very strong. Well, 0.93, think of these like test grades. 0.93, that would be an A. That's very strong. If I was in the 80s, that's still strong. That's great. If I was in the 70s, C's are still good. All of those things would be reasonably strong. It's when you get into the 60s and the 50s that you go to like moderate, so-so. And then when you get into the lower F's, those would be extremely weak or no correlation. So when I ask this question here, is it appropriate to make predictions, I'm looking at R. And yes, since R is relatively high, we would say yes. When I write the linear regression equation, on the printout it says y equals a plus bx, and then it gives you an a and a b. Now obviously you're going to want to round those off. So I rounded off to 2 decimal places. And the other thing is, when I write the linear regression model, I use a y with a hat on it. Calculator just says y equal, but it's actually a y with a hat. My a, when I round it off to 2 decimal places, is negative 16.44. My b is positive, so I put a plus sign in there. If I round that b off to 2 decimal places, that rounds off to 0.80, and you have your x. Now, we didn't do this in class today. It's really for part 2, but since it's on the slide, I'll go ahead and do it. If I want to know 22 police patrols, how many gallons of gas could I predict I would use? In my calculator, I would type in negative 16.44 plus 29.80, and for x, I would just type in times 22, and I would round that off to the nearest whole gallon. My variables, x is still the number of police patrols, y this time is the number of trips to the dentist office. Do you think there's going to be any correlation there? Well, if I look at the picture, don't make stuff up, okay? If you don't see a pattern of a straight line, don't search it out. It's not there if you can't see it. So, since I don't see a pattern, that doesn't look like a linear relationship. But if I want to be sure that I'm not ignoring something, compute your R, and that's 0.106, 107, 0.107. That's 10%. No. That's definitely a no. And if it's a no, we don't care about part 3. This time, X is the number of police patrol, Y is the number of burglaries. With this, we would hope there's a relationship, and we would hope that more police would make fewer burglaries. When we look at the graph, that's definitely a pattern. This pattern goes down from left to right. Down. That means it's going to be a negative relationship, but it's still a relationship. I got my ln regs here that I can write the equation. And when I look at my R, one of the things that we saw that I didn't bring up, when I had a positive relationship, meaning the line went up from left to right, R was positive. Now that it goes down from left to right, the negative reflects the direction. The number is still the same strength, whether it's positive or negative. It just tells you the direction is down. So 86 is a B. Yes, I should be able to make predictions if I want to. I write out my regression line. If I want to do the last part, I take out the X and I put in times 22 and round it off. These next pages, you want to check these on the PowerPoint. I'm not going to go through all these, but this is where you're going to push buttons. I'm going to leave this for you to do on your own. There are calculator directions on D2L that you can follow. I don't think it's for this example, but it'll tell you how to push the buttons to get your data into L1, L2, that you should already know, but how to make your calculator make a scatter plot, how to make it graph the line in it. Go to D2L, figure out how to push the buttons on your calculator, and then do these 5 problems. I have the answers to the concepts that you will look at after you do those sample problems. Basically, we're trying to figure out when the regression line is positive, correlation coefficient, that's your R, is also positive. If it's negative, your R is negative. If the regression line is 0, then your R is 0. An R is 0 means that your line should be a horizontal line. It goes straight across. That means there's no correlation. And another way of saying that, slope of the regression line and the correlation coefficient, they have the same sign. Here, I'm just trying to make the point that if you have R squared is whatever R is squared. So 1 squared is 1, but R squared is a percent. R squared is a percent. You can express it as a decimal, but it is a percent. When you square a negative, you get a positive answer, unless you square it incorrectly. If you type in negative 0.2 squared on your calculator without parentheses, the answer to that is negative 0.04. That's called operator error, because order of operations says if you want to square negative 0.2, you have to put parentheses around it, otherwise you're not going to get a positive answer. So we need to square the entire thing, the negative and all, either use parentheses or know that R squared is never negative. Now what it means is this. When you look at Y, the variability in Y is explained by whatever percentage you have of variation in X. Let's look at those sentences. Variability in Y, another word for that is just the change. Variation in X is again another word for change. So what we're saying here is if we have a perfectly linear slope, the correlation coefficient would be 1. That means 100% of the change in Y can be explained by the change in X. 18 is the same thing, except if it's a negative slope, your correlation coefficient is negative 1, but that's still 100%. And the closer you are to negative 1 or positive 1, the more variation in Y is explained by X. Now up here, if this is your R, you square it to get the percentage. So 73.9%, 73.96% of the change in Y is explained by the change in X. If I square 0.36, that's 12.96% of the change in Y is explained by the change in X. We'll talk about this more in the context of a problem when we get back to class on Wednesday.